Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about Introduction to Superconductivity and BCS theory for it. In this lecture video, I will discuss about properties of superconductors. So let's get started. The content of this lecture video is as follows. I will discuss about properties of superconductors, which includes zero electrical resistance, persistent current, critical temperature, critical magnetic field, critical current, Meissner Effect, London penetration depth, flux quantization, entropy, and finally I will discuss about isotope effect. Let's see first property of superconductor, that is zero electrical resistance. The most obvious characteristic of superconductor is the complete disappearance of its electrical resistance below a temperature that is known as its critical temperature. Experiments have been carried out to attempt to detect whether there is any small residual resistance in the superconducting state. A sensitive test is so start a current flowing around a superconducting ring and observe whether the current decays. The current flowing in the superconducting loop clearly cannot be measured by inserting an ammeter into the loop, since this would introduce a resistance and the current would rapidly decay. The simplest method to measure the electrical resistance of a sample of some material is to place it in an electrical circuit in series with a current source I and measure the resulting voltage V across the sample. The variation of resistance of superconductor with temperature can be measured by four-probe method. The current is passed in superconductor through current probes 1 and 4 as shown in this diagram. Voltage developed is measured with voltage probes 2 and 3. The resistance of the sample is given by Ohm's law as R is equal to V upon I. If the voltage is 0, this means that the resistance is 0. A graph of resistivity versus temperature for a superconductor shows a sharp transition to 0 at the critical temperature Tc. Behavior of resistivity for superconductors at superconducting phase, that is the transition temperature Tc, which is shown in red line, and for the normal metal, for the normal state, which is shown in blue line. In superconducting materials, the characteristics of superconductivity appears when the temperature T is lowered below critical temperature, that is Tc, which is as shown in diagram. The value of this critical temperature varies from material to material. For normal state, a voltage is developed across the voltage probe and Ohm's law V is equal to IR is obeyed. Similarly, for the superconducting state, the resistance of superconductor vanishes, that is R is equal to 0, and hence the voltage across voltage probes disappears, that is V is equal to 0, while current continues to flow. This is the method to observe zero electrical resistance in superconductors in superconducting state. Now let's see second property of superconducting material is persistent current. When a ring of superconducting material is placed in magnetic field at critical temperature and suddenly magnetic field terminated, then the current starts flowing through the closed loop. Once a current is started in a closed loop of superconducting material, it will continue to keep flowing of its own accord around the loop as long as the loop is held below critical temperature, where T is less than Tc. Such a steady current which flows without diminishing in strength is called persistent current. The persistent current does not require external power to maintain. In superconducting state, resistance is 0 and thus there are no I square R losses. Once the current flow is initiated, it is estimated it persists for more than 10 raised to 5 years. Persistent current is one of the most important property of superconductor. Superconductor coils with persistent current flowing through them produce magnetic fields and can therefore act as a magnets. Schematic representation of a persistent current in a mesoscopic metal ring threaded by a magnetic flux quantum phi is shown in this diagram. For rings nearly 1 micrometer in size and at a temperature nearly 1 Kelvin, the flux quantum induces a persistent current due to the Aharonov-Bohm effect. Elastic scattering from static impurities, that is light blue spheres, does not destroy the phase coherence of the wave functions, and persistent currents can flow even though the metal has a finite resistance. The phase coherence of the electron waves is more sensitive to spin flip scattering from magnetic impurities shown in red arrows. However, while a concentration of 1 ppm magnetic impurities would be enough to destroy superconductivity in these metal rings, it is not sufficient to quench persistent currents in the normal state. A typical ring current is 1 nanoampere for a ring diameter of 0.6 micrometer at a temperature below 0.5 Kelvin. A scanning electron microscope image of a mesoscopic metal ring is shown in this numeric diagram. Now let's see third property of superconducting material is critical temperature, represented by capital T subscript C. The critical temperature of superconductors is the temperature at which the electrical resistivity of a metal drops to zero. The transition is so sudden and complete that it appears to be a transition to different phase of matter. This superconducting phase is described by the BCS theory. Several materials exhibit superconducting phase transitions at low temperatures. The highest critical temperature was about 23 Kelvin until the discovery in 1986 of some high temperature superconductors. Materials with critical temperatures in the range 120 Kelvin have received a great deal of attention because they can be maintained in superconducting state with liquid nitrogen 77 Kelvin. This table shows critical temperatures for different materials, which includes gallium 1.1 Kelvin, aluminium 1.2 Kelvin, indium 3.4 Kelvin, tin 3.7 Kelvin, mercury 4.2, lead 7.2, and niobium 9.3 Kelvin are the critical temperatures of respective materials. Now let's see next property of superconducting material is critical magnetic field, which is represented by capital H subscript C. The superconducting state cannot exist in the presence of magnetic field greater than a critical value, even at absolute zero. This critical magnetic field is strongly correlated with the critical temperature for the superconductor, which is in turn correlated with the band gap. The critical magnetic field refers to the maximum magnetic field strength below which a material remains superconducting. It depends on temperature. Superconductivity is characterized both by temperature and magnetic field. Changes in either temperature or magnetic field can cause the phase transition between normal and superconducting state, which is shown in this graph. The highest temperature under which the superconducting state is seen is known as the critical temperature. At that temperature, even the weakest external magnetic field will destroy the superconducting state. So the strength of the critical field is zero. As temperature decreases, the critical field increases generally to a maximum at absolute zero. The critical magnetic field at temperature capital T is given by HCT is equal to HC0 in bracket 1 minus in bracket T upon TC bracket square bracket complete, where SC0 is the critical magnetic field at 0 Kelvin and TC is the critical temperature. The critical magnetic field required to destroy the superconducting state is strongly correlated with the critical temperature for superconductors. Each of these parameters can be viewed as representative of energy which can be supplied to the material in such a way that it interferes with the superconducting mechanism. This is consistent with the idea that there is a band gap between the superconducting and normal state. This graph shows critical magnetic fields for few materials in which critical field Hc0 at different critical temperature Tc for few materials. For example, niobium 198 millitesla, lead 80.3 millitesla, and tin 30.9 millitesla are shown in this graph. Based on critical magnetic field, let's see one numerical. The transition temperature of lead is 7.2 Kelvin. However, at 5 Kelvin, it loses the superconductivity property if subjected to magnetic field of 3.3 into 10 raised to 4 ampere per meter. Find the maximum value of H which will allow the metal to retain its superconductivity at 0 Kelvin. The solution of this problem is as follows. We have formula HCT is equal to HC0 in square bracket 1 minus in bracket T upon TC bracket square bracket complete. So rearranging this equation, we can write HC0 is equal to HCT upon 1 minus T square upon TC square. Therefore, by simply putting the values in this formula, we can have Hc is equal to, HCT is given 3.3 into 10 raised to 4 ampere per meter divided by 1 minus, first temperature is 5 degree Kelvin and second one, that is critical one, is Tc is given 7.2. So we can write 1 minus 5 square divided by 7.2 square. Therefore, we can write 3.3 into 10 raised to 4 ampere per meter divided by 1 minus 25 upon 51.28. Simply by solving this equation, we can have Hc0 is equal to 6.37 into 10 raised to 4 ampere per meter. This is the value of critical magnetic field. Now let's see one more example related to this. The critical field of niobium is 1 into 10 raised to 5 ampere per meter at 8 degree Kelvin and 2 into 10 raised to 5 ampere per meter at 0 Kelvin. Calculate the transition temperature of niobium. The solution of this problem is as follows. We have the same formula. HCT is equal to HC0 in bracket 1 minus in bracket T upon TC bracket square bracket complete. So rearranging this equation to the Tc, that is critical temperature, Tc is equal to capital T upon 1 minus HCT upon HC0 bracket raised to half. So simply putting the values in this formula, Tc is equal to, temperature is 8 Kelvin divided by 1 minus 1 into 10 raised to 5 ampere per meter, which is HCT, and second one is HC0, that is 2 into 10 raised to 5 ampere per meter bracket raised to half. So after solving this equation, we get Tc is equal to 11.3 Kelvin, which is the critical temperature of niobium. Now let's see the next property of superconducting material is critical current. An electric current flowing through a superconducting material produces a magnetic field surrounding to it. As current increases, the associated magnetic field also increases. Thus, it is important to have current flowing through the superconductor below a certain critical value of IC, which is associated with critical magnetic field Hc. Current density is defined as current per unit area. The current density associated with critical current is called critical current density, that is Jc. It is the maximum current density at which the superconductivity disappears. For the value of J is less than Jc, the current can sustain itself. This effect was observed in 1916 by Silsby and is known as Silsby's effect. A superconducting ring of radius capital R ceases to be a superconductor if the critical current exceeds IC is equal to 2 pi capital R into capital HC. If the current is superconductor is increased beyond critical current, the associated magnetic field will exceed critical magnetic field at C, and superconductor may destroy its own superconductivity. The existence of critical current sets a definite limit to the size of the current that can flow through a superconducting coil without disturbing the superconducting state. The maximum current that a superconductor can carry decreases as the temperature is raised and falls to zero at the transition temperature of the material. Since the critical current falls with temperature, the critical magnetic field will also decrease as the transition temperature is approached. The variation of critical current density and critical magnetic field with temperature is shown here in this diagram. Now let's see one numerical which is based on critical current. The critical magnetic field at 5 degree Kelvin is 2 into 10 raised to 3 ampere per meter in superconducting ring of radius 0.02 meter. Find the value of critical current. The solution of this numerical is as follows. We have critical current formula. IC is equal to 2 pi R HC. The value of R is given and the value of critical magnetic field is given. So by simply putting these values in this formula, we can write HC is equal to 2 into the value of pi 3.143 into the value of radius of the ring 0.02 meter into 2 into 10 raised to 3 ampere per meter, which is the critical magnetic field. After solving this, we get the critical current IC is equal to 251.4 ampere. Now let's see one more numerical. Calculate the critical current for a wire of lead having a diameter of 1 millimeter at 4.2 Kelvin. The critical temperature for lead is 7.18 Kelvin and the critical magnetic field HC is equal to 6.5 into 10 raised to 4 ampere per meter. The solution of this problem is as follows. We have formula HCT is equal to HC0 in square bracket 1 minus in bracket T upon HC bracket square bracket complete. Therefore, simply by putting the values in this formula, we can write HCT is equal to 6.5 into 10 raised to 4 ampere per meter in bracket 1 minus in bracket 4.2 Kelvin divided by 7.18 Kelvin bracket square bracket complete. After solving this, we get HCT is equal to 4.28 into 10 raised to 4 ampere per meter. Now let's find out the critical current with the formula IC is equal to 2 pi R HC. Therefore, we can write IC is equal to pi small d HC. Small d is the diameter. Therefore, IC is equal to 3.14 into 1 into 10 raised to minus 3 meter into 4.28 into 10 raised to 4 ampere per meter. Simply by solving this, we get IC is equal to 134.5 ampere. This is the value of critical current. Now let's see next important property of superconductor material is Meissner's effect. When certain superconductors are cooled below critical temperature, T is less than Tc, in presence of external magnetic field, magnetic flux is expelled from the interior of the superconductor and it becomes perfect diamagnetic. This phenomena is called Meissner's effect. A material drops below its superconducting critical temperature. Magnetic fields within the material are expelled via the Meissner's effect. The conditions at normal state, that is temperature T is greater than temperature Tc, that is critical temperature, and the superconducting state, that is T is less than Tc, with external magnetic field capital B is shown in this diagram. External magnetic fields cannot penetrate a superconductor due to Meissner's effect. The induced field showed in green color and induced current showed in red color are shown here in this diagram. Now let's see two important conditions for Meissner effect. Let's say first, at temperature is greater than the critical temperature, that is T is greater than Tc. The material is in normal conductor state and not a superconductor. When a magnetic field is applied to it, it penetrates through the material. If capital H is external magnetic field and capital M is magnetization produced within the sample, then magnetic induction inside the specimen capital B is given by capital B is equal to mu naught in bracket H plus M. Now let's see the second condition. At T is less than Tc, that is temperature is less than critical temperature, the material turns a superconductor, and as magnetic field is expelled out of superconductor, the magnetic induction inside the material will be B is equal to 0. Therefore, above equation can be written as 0 is equal to mu naught in bracket H plus M. So, by simply rearranging this equation, we can write M is equal to minus H. That is, magnetization produced in the sample is equal to negative value of external magnetic field. Now let's see the magnetic susceptibility. Magnetic susceptibility is the degree of magnetization of a material in response to an applied magnetic field. If the magnetic susceptibility is negative, the material is called as a diamagnetic. For superconductors, magnetic susceptibility of material is Xi is equal to M upon H. So here the value of M is minus H. So simply by putting this value, we can write Xi is equal to minus H upon H. That is equal to minus 1. Therefore, Xi is equal to minus 1. This indicates that superconductors are perfect diamagnetic because the magnetic susceptibility value is negative here, which is minus 1. So this is one important property of superconducting material, is that superconducting materials are perfect diamagnetic materials. Now let's see the perfect diamagnet, which is shown in this diagram. If a conductor already had a steady magnetic field through it and was then cooled through the transition to a zero resistance state, which becoming a perfect diamagnet, the magnetic field would be expelled to stay at the same. So this is shown in this diagram. Now similarly, let's see for the superconductor state, which is shown in this diagram. Remarkably, the magnetic behavior of a superconductor is distinct from the perfect diamagnetism. It will actually exclude any magnetic field present when it makes the phase change to the superconducting state, which is shown in this diagram. So this is the comparison between the perfect diamagnet and perfect superconductor according to these two diagrams. Now let's see next important property of superconducting material is London penetration depth. As shown in this diagram, the London penetration depth refers to the exponentially decaying magnetic field at the interior surface of the superconductor. It is related to the density of superconducting electrons in the material. The fact of exclusion of magnetic fields from the interior of the superconductor is called as the Meissner's effect, which we have already discussed before. When a magnetic field is applied to superconductor, the applied field does not suddenly drops to zero at the surface. Instead, the field decays exponentially according to the formula Hx is equal to H0 exponential of minus x divided by lambda, where H0 is the applied field at the surface at x is equal to 0 and x is the distance from the surface. The length lambda is called the London penetration depth. It may be defined as the effective depth to which a magnetic field penetrates a superconductor. This is called as a London penetration depth and which is represented by lambda. In superconductors, the London penetration depth, usually denoted by lambda or lambda subscript capital L, characterizes the distance to which a magnetic field penetrates into superconductor. Typical value of lambda L ranges from 50 to 500 nanometer depending on the material. It is independent of frequency of magnetic field, but it is strongly depends on temperature. The temperature dependence of lambda, that is London penetration depth, is given by the relation lambda T is equal to lambda 0 divided by under root of in square bracket 1 minus in bracket T upon Tc bracket complete raised to 4. where lambda T and lambda 0 are the penetration depth at temperature T and at temperature 0 degree Kelvin. The lambda increases with the increase in temperature, and at the critical temperature it becomes infinite. At T is equal to Tc, that is temperature is equal to the critical temperature, the material goes into the normal state and hence the magnetic field penetrates the whole specimen. So here is the importance of London penetration depth. Now depend on London penetration depth, let's see one numerical. Calculate the penetration depth of lead at 5.2 Kelvin if the London penetration depth at 0 Kelvin is 37 nanometer. The critical temperature of the lead is 7.193 Kelvin. The solution for this numerical is as follows. We have formula lambda T is equal to lambda 0 divided by under root of in square bracket 1 minus in bracket T upon Tc bracket raised to 4. So rearranging this formula, we can write lambda T is equal to lambda 0 in bracket 1 minus in bracket T upon Tc bracket raised to 4 square bracket complete raised to minus half. Therefore, lambda T is equal to lambda 0's value 37 nanometer in square bracket 1 minus T's value is 5.2 Kelvin divided by Tc is 7.193 Kelvin bracket complete raised to 4 square bracket complete raised to minus half. So simply by completing this equation and calculating this equation, we can write lambda T is equal to 43.4 nanometer. So this is the London penetration depth. Now let's see the next property of superconducting material is flux quantization. In 1957, Alex C. Abrikosov, a scientist, predicted the existence of magnetic flux quanta. The diagrammatical representation of flux quantization is shown in this diagram. According to scientist Abrikosov, a closed superconducting loop can enclose magnetic flux only in integral multiples of fundamental quantum of flux. The magnetic flux superconducting ring is given by phi is equal to small n into small h upon 2e, that is equal to n into phi naught, where small n is equal to 0, plus minus 1, plus minus 2, plus minus 3 and so on. Since here phi naught is equal to h upon 2e, which is flux quantum and is called fluxon. The value of fluxon is phi naught is equal to 2.07 into 10 raised to minus 15 Weber. So this is the flux quantization. Now let's see next property of superconducting material is entropy. We know that the entropy is a measure of the disorder of a system. In all superconductors, the entropy decreases significantly on cooling below the critical temperature Tc. Therefore, the observed decrease in entropy between the normal state and the superconducting state shows that the superconducting state is more ordered than the normal state. For aluminium, the change in entropy was observed to be small, of the order of 10 raised to minus 14 into small k per atom. In this, small k is the Boltzmann constant. The variation of entropy of aluminium in the normal and superconducting states with temperature is shown in this diagram, which shows that as temperature goes on increasing for the normal state, the entropy increases linearly. But whereas for the superconducting state, the entropy increases with some curve-shaped line. Now let's see the last property of superconducting material is isotope effect. The phenomena of decrease of critical temperature with increasing isotopic mass is called as isotopic effect. In 1950, C.A. Reynolds and E. Maxwell found that the critical temperature decreases with increasing isotopic mass capital M. The variation is given by the relation Tc is directly proportional to the capital M raised to minus alpha. Therefore, we can write m raised to minus alpha into Tc is equal to constant, where alpha is constant and is approximately equal to half. Since the mean square of amplitude of atomic vibrations is proportional to under root of capital M at low temperatures, Above equation suggests that the lattice variations are involved in causing superconductivity. The value of alpha can be expressed as alpha is equal to minus diaba into ln Tc divided by diaba into ln m. The change in isotopic mass does not change in electronic structure. Dependence of transition temperature on the isotopic mass suggests involvement of electron lattice interaction. Figure shows the experimental results for tin, which shows that as isotopic mass increases, the critical temperature goes on decreasing linearly. Now let's see one problem which is based on isotopic effect. In a superconducting material, isotopic mass is 199.5 AMU and critical temperature is 5 degree Kelvin. Calculate the isotopic mass at 5.1 Kelvin. The solution of this problem is as follows. We have formula Tc is directly proportional to 1 upon under root of capital M. Therefore, we can write T1 under root of M1 is equal to T2 under root of M2. Rearranging this equation, we can write M2 is equal to M1 in square bracket T1 upon T2 square bracket complete bracket raised to. So we have the values M2 is equal to M1's value is 199.5 AMU, which is isotopic mass M1, into bracket 5 degree Kelvin divided by 5.1 degree Kelvin bracket raised to, that is bracket square. Therefore, calculating this equation, we can have isotopic mass at 5.1 degree Kelvin is M2 is equal to 191.68 AMU. So this is the solution of this problem. This is all about properties of superconductors. In next lecture video, I will discuss about types of superconductors. So please don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.